Hello my scholars, you are welcome to my school YouTube channel and my name is Frank. In today's video we are going to be focusing on structure of the atom. Okay, and under the structure of the atom we are going to be looking at energy quantization, okay, and other related topic. So relax, do not go anywhere, I'll be right back. Well, welcome back to my school YouTube channel. Like I said earlier, we are going to be looking at the structure of the atom. So before we begin with the lesson, let's quickly run through the objective for today's video lesson. So objective number 1, explain the concept of energy quantization. 2, use the photon concept to explain the ejection of electrons in the photoelectric effect. 3, describe X-ray production and state its characteristic properties, uses and safety precaution. Then 4, solve simple problems involving threshold frequency, work function, and Planck's constant. So let's begin with our lesson. So the concept of energy quantization comes from Bohr's atomic model, which states that electrons occupy discrete, that is quantized energy levels, and Planck's theory of radiation. And this theory says that energy is emitted in separate discrete packets known as quanta. So the energy of one quantum of radiation, in bracket photon energy, is given by E is equals to hf, where h is Planck's constant and f is the frequency of radiation. So the whole idea of energy quantization means that radiated energy is not continuous but exists only in discrete amounts with no values in between. Okay, so the energy level values are expressed in terms of whole number, okay, represented with letter n, which can be 1, 2, 3, 4, and so on. N is called the quantum number for a particular energy level. Thus, according to Planck's quantum hypothesis, the energy of radiation can be E is equals to H1, that is for the first energy level. Then for the second energy level, we have 2H2 or 2HF or 3HF for the third energy level, etc. Okay, so now let's talk about energy levels in an atom. So remember that electrons in atoms are arranged around their nuclei in positions known as, let's move to the next slide, in positions known as electron orbits or energy levels. Each electron is held in its orbit by a force of attraction between it and the nucleus. Thus, energy is required to raise an electron from one energy level to a higher energy level. So in that case, we say the atom is excited, okay, and energy, in bracket photon, is released when an electron falls from one energy level to a lower energy level, and in that case we say emission. Okay, so an atom is excited when it is heated or bombarded with an energetic particle. For example, the nucleus of an atom can be bombarded with a neutron. Okay, so energy levels are usually represented by horizontal lines drawn on a vertical scale as shown in the diagram below. So what we have in the diagram below is for hydrogen atom, that is the energy level of hydrogen atom. And as you can see in the diagram, you see that as the energy level increases, the space between the energy levels decreases. Okay, and one of the reasons for that is because when an atom is further away from the nucleus, okay, the force of attraction becomes weaker. Okay, and those electrons that are further away from the nucleus, the energy level is almost the same. Okay, that is, there's just a little difference between them. Okay, and that's exactly what you are seeing around here. Okay, so let's move to the next slide. Now at the ground state, that is when n, that is the quantum number, when the quantum number is equal to 1, and this is the lowest energy level corresponding to minus 13.6 eV. Okay, so that eV actually stands for electron volts. Okay, and that is that minus 13.6 eV is equals to minus 21.8 times 10 raised to the power minus 19 joules. Okay, for the hydrogen atom. And it is at this lowest level that the hydrogen atom is most stable. Okay, that means at this stage or at this point it's not excited. Okay, so the higher energy levels are also calculated from the formula minus 13.6 eV all over n squared, where n is equals to 1, or where n can be 1, 2, 3, 4, etc. Okay, so when an atom is raised from the ground state to any of its higher energy levels, it is said to be in an excited state. Okay, so the energy required to raise an atom from its ground state to an excited state is called excitation energy, and it is represented by letter EX. Okay, given by ES is equals to En minus E naught in bracket EV. Okay, and also ES is equals to EVX, where E is equals to electronic charge, Vx is equals to excitation potential of the atom. At the ionization level, the energy value becomes 0. That is, for a hydrogen atom, the value of the energy level increases from minus 13.6 eV at the ground state to 0 at the ionization level, making the ionization energy to be 13.6 eV when the electron or atom is given an amount of energy equal to the ionization energy. The electron is just able to become a free electron. If the electron is given a greater amount than the ionization energy, the excess energy is converted. So basically, what happened here is just like dealing with your number line. Okay, so you actually move 13 steps, okay, to your right, so that at the ground state, that is when the energy level increases from minus this, okay, at the ground state to 0, okay, you actually move 13 times, just like you are moving on your number line from minus 13.6 towards 0. Okay, so basically that is what is happening here. So the excess energy is converted. Let's move to the next slide. So the excess energy is converted to kinetic energy of the free electron outside the atom, and this is also equal to the kinetic energy of the free electron that is outside the atom. So the ionization energy, AI, is the energy required to remove an electron completely from an atom in its most stable state. Okay, so this ionization energy is given as E infinity minus E naught is equals to EVI, and this is also equals to HC over lambda I, where VI is equals to ionization potential, lambda I is equals to wavelength corresponding to ionization potential. Now, because excited states are unstable, electrons will jump back to its original energy level or orbits and emit a photon or quantum of light in the process. So the equation for the emission of the photon is given by delta E is equals to En minus E naught, and this is also equals to HFN. Okay, but remember that F is equals to C all over lambda. So in place of F, we just replace it with C all over lambda, so that this delta E is also equals to HC all over lambda N. Okay, where En is equals to energy in the excited state, while E naught is equals to energy in the ground state. H, as we know, is Planck's constant, and C corresponds to speed of light, of course, speed of light in vacuum, okay? While Fn is equals to frequency of emitted photon, while lambda n is equals to wavelength of the radiation. So let's move to the next slide. Now, this relation is still applicable when the electron falls to a lower energy level, which is not the ground state. So sometimes electron can fall from a high energy level to another energy level that is not a ground state, right? But this formula still applies, okay? So delta E is equals to En minus Em. That is also equals to HF. And remember, F is equals to C over lambda. So in place of F, we replace it with C over lambda, so that delta E is also equals to HC all over lambda, okay? So let's see some examples. So let's start with example 1. An electron excited to an energy level E2 is equals to minus 2.42 times 10 raised to the power minus 9 joule, falls to the ground state E0 is equals to minus 21.8 times 10 raised to the power minus 19 joule. Calculate the I frequency, II wavelength of the emitted photon. Then H is given to us to be equal to 6.6 times 10 raised to power minus 34 joule second. C is equals to 3.0 times 10 raised to power 8 meter per second. Now remember that C represents the speed of light, okay? So solution. Now remember that the electron was actually excited, okay, to an energy level E2, okay, from the ground state, and the energy, that is the electron, okay, actually fell from E2 and excited energy level E2 to the ground state, right? So in that case, we are going to be having E2 minus E0, okay, because this is where the falling starts from, or this is where the movement of the electron started from. So, and this is also equals to HF, right? Now, remember, we are looking for frequency. So here, we can simply divide both sides by H to get the value of frequency. Now, remember that E2 is equals to minus 2.42 times 10 raised to power minus 19, okay? Then E0 is equals to minus 21.8 times 10 raised to power 19. So in place of E2 and E0, we replace them with those figures. Okay, so if we do that, so if we substitute into this formula, we'll be having minus 2.42 times 10 raised to power minus 19 minus then minus 21.8 times 10 raised to power minus 19, and this will be equals to 6.6 times 10 raised to power minus 34. Now remember that 6.6 times 10 raised to power minus 34 represent the value of Planck's constant, okay, times F. So since we are looking for F, we simply divide both sides by 6.6 times 10 raised to power minus 34, right? So if we do that, F will be equals to 2.9 times 10 raised to power 15 hertz. Now remember that the unit of frequency is hertz, okay, or frequency is measured in hertz. Okay, now for the second one, we are asked to calculate for the wavelength. Now remember that F is equals to C all over lambda. So from there, we can actually calculate for the wavelength, right? But remember that F is equals to C all over lambda. Now we know F, which we have calculated in I part of this question. So the value of C is given to us. So from here, we can simply make lambda the subject of formula by simply exchanging the position of lambda, okay, with that of F. So if we do that, we'll be having lambda to be equals to 3.0 times 10 raised to power 8 divided by 2.9 times 10 raised to power 15, right? So if we divide, we'll be having 1.03 times 10 raised to power minus 7 meters. Okay, remember lambda is given in meters. It is just the difference between two troughs, right? The distance between two troughs or two crests. That is what is referred to as lambda. So that's why the unit, okay, is given, or that's why it is measured in meters. So just take note of that. So let's move to the next slide to see another example. Okay, so the ionization potential of the hydrogen atom is 13.6 volts. Calculate the minimum wavelength of the radiation the hydrogen atom can emit. So here we are given electronic charge E to be equals to 1.60 times 10 raised to power minus 19 coulomb. Planck constant is equals to 6.63 times 10 raised to power minus 34 joule second. And we are given C to be equals to 3.0 times 10 raised to power 8 meter per second. Okay, so solution. Now to solve this, we are using this formula EVI is equals to HC all over lambda I. Basically because we are talking about ionization potential. Okay, and remember that the ionization potential at this point also corresponds to the wavelength, okay, correspond to the ionization wavelength of the radiation, right? So here we just substitute. Now we are giving E to be equals to 1.60 times 10 raised to power minus 19 coulombs. So in place of E, we replace it with that figure, then times VI, which is given to us. Mind you, VI is the ionization potential of the hydrogen, and is given to us to be equals to 13.6. So here we fix 13.6, and that will be equals to, now we are giving H and we are giving C in this question. So the only thing that is missing, that is what we are calculating for, is the ionization wavelength, right? So what we basically do here is just to switch the position of this figure with lambda I. So if we do that, we'll be having 6.63 times 10 raised to the power minus 34 times 3.0 times 10 raised to the power 8 divided by 1.60 times 10 raised to the power minus 19 times 13.6, right? So when we divide, we'll be having 9.14 times 10 raised to the power minus 8 meters. So remember, we are calculating for the ionization wavelength, okay? So now let's move on to Franck-Hertz experiment. So James Franck and Gustav Hertz found a direct experimental evidence of the existence of atomic energy levels. They bombarded atoms in the form of mercury or sodium vapor with electrons emitted from a hot filament F towards a ground plate G. So let's move to the next slide so we can see the diagram. So basically, this is the diagram, okay? And this is the graph of the current against the voltage. So the number of electrons per second reaching the anode A, which is this point, was measured by an electrometer E. Okay, so basically this is what is happening inside the device, inside the electrometer that you are seeing on the screen. So the electrons are accelerated towards the ground plate G. So this is the ground plate G, okay, and the electrons are accelerated towards it. Now the distance between F and G is arranged to be much greater than the mean free path, that is, mean distance between atomic collision, in bracket, to ensure that the electrons would make collision before reaching G. So the reason for that is so that to ensure that the electrons will collide, okay, before they get to the ground plate, okay. Now, with the potentiometer P, which is this, the potential difference V between F and G can be varied. So as the potential difference increases from 0, the acceleration of the electron increases, which implies that the current I increases too, okay? Let's move to the next slide. Now, I increases as the potential difference increases until it gets to a certain peak value. When the potential difference equals V1, as the potential difference is further increased, the current I drops to a certain minimum level and rises again to another peak value when the PD equals V2. So this pattern of drop and rise in the current was repeated as V was further increased. So a graph of current against voltage is as shown above, just like the graph I've seen, okay? So it was found that the potential interval between successive peaks was constant. This constant potential interval between successive peaks is known as the excitation potential, Vc, okay, of the atom, and it is 2.1 volts for sodium vapor. Okay, so now let's talk about atomic spectra. So for atomic spectra, you are simply referred to the characteristic patterns, okay, of light emitted or absorbed by atoms. Okay, that's basically what atomic spectra means. Okay, so there are two classes of atomic spectra, namely emission spectra and absorption spectra. So when we are talking about emission spectra, we are talking about when or where light is given out by a source. Okay, let's move to the next slide to talk about absorption spectra. Now, when we are talking about absorption spectra, we are talking about where light from a source is absorbed when it passes through another material. The material is usually a gas, okay, or a liquid. Now, let's talk about the different types of emission spectra, okay? Now, remember, we are saying for emission spectra is when light is given out from a source. So now we have three types of emission spectra, namely line spectra, band spectra, and continuous spectra. So each of these three types of emission spectra, we are going to be explaining them one after the other. So let's begin with line spectra. So line spectra can also be referred to as emission line spectra. And basically it consists of distinct and separate bright lines of definite frequency or wavelength on a dark background. So the color of the spectra is a characteristic of the source. It is emitted by a monoatomic gas such as hydrogen in a distant tube and sodium salt vaporized in a Bunsen burner or in a Bunsen flame. Okay, so line spectra is evident for the existence of quantized energy levels in an atom. Now let's talk about band spectra, okay, which is the second type of emission spectra. Okay, so band spectra consists of a series of bands and are essentially due to molecules. So the different band heads in a band system are due to small allowed discrete energy changes in the vibrational energy of the molecule. Let's move to the next slide. They are emitted by gases, molecules, okay, in brackets, gases, molecules, such as oxygen, carbon dioxide, carbon monoxide in a discharge tube, okay? So let's talk about continuous spectra. So continuous spectra consists of emissions of radiations of all different wavelength or color. Continuous spectrum is emitted by hot solids with temperatures above 800 Kelvin. A piece of iron heated in a flame, incandescent solids, and the sun, they all emit continuous spectra. Okay, now let's talk about the second type of atomic spectra, which is absorption spectra. So absorption spectra is also known as, or is also referred to as, line absorption spectra. Okay, so they are obtained when light passes through a cool gas and certain wavelengths of the light are absorbed. This gives series of dark lines, each corresponding to one of the wavelengths absorbed. So absorption occurs by the electrons in the atom absorbing the energy from the incoming radiation and then radiating it in all directions. So the wavelengths appear dark when compared with the rest of the spectrum. Atoms can absorb energy in the following ways. Okay, so let's move to the next slide to see how atoms can absorb energy. Okay, so atoms can absorb energy in the following way. 1, inelastic collision with energetic molecules in a flame. 2, inelastic collisions with bombarding electrons in a discharge tube. And 3, from photons. Okay, so the dark lines in sun's visible spectrum are due to the absorption of photons. Atoms in the cooler part of the sun absorb these photons and are excited. Now let's talk about color and light frequency. Okay, the frequency and color of light given off by an excited atom of an element is unique to that element. Okay, basically that is just the idea here. Okay, the frequency and color of light given off by an excited atom of an element is unique to that element. Okay, excited atoms emit light of only certain characteristic frequencies or color. Thus, the frequency and the color of light emitted depends on the source. So, e.g., if we have a sodium vapor, okay, the sodium vapor will emit yellow-orange light, and krypton atom emits a photon of orange light. But remember, the vapor here is as a result of the sodium, and sodium is the element. Okay, so it is actually the element that determines the color and the frequency. Okay, so here we are just talking about the source. So the source of the emission here is sodium vapor. So sodium vapor will emit yellow-orange light, while that of krypton atom will emit a photon of orange light. Now let's talk about fluorescence. Okay, so fluorescence, this is a phenomenon in which an atom absorbs a photon in the ultraviolet region to reach an excited level and then drops back to the ground level in steps, emitting 2 or more photons with smaller energy or longer wavelength. Or simply you can put it as substances or materials, okay, that absorb light at certain frequency, okay, and almost immediately re-emit it at a longer frequency. Basically, that is what fluorescence means. So let's move to the next slide. Now here, let's talk about the photoelectric effect, right? So photoelectric effect is the phenomenon in which electrons are emitted from the surface of a metal when radiation of appropriate frequency strikes the metal surface. Okay, so the emitted electrons are known as photoelectrons. Okay, and the liberated electrons absorb energy from the incident radiation and are thus able to overcome the attraction of positive charges. Now let's see some facts about photoelectric effects. Okay, so one of them is that Leonard in 1902 found that the maximum kinetic, please take note that this part is very, very important. Okay, now Leonard in 1902 found that the maximum kinetic energy or maximum velocity of the emitted electron was independent of the intensity of the incident light. but was proportional to its frequency. Okay, meaning that the higher the frequency, then the higher the maximum kinetic energy or the maximum velocity. But that this maximum velocity or maximum kinetic energy does not depend on the intensity of the incident light. Okay, now they also found out that there exists a threshold frequency F0 for all surface. Okay, so for all metal surfaces there exists a threshold frequency, and below this frequency no electron is emitted no matter the intensity of the radiation. Okay, so no matter the intensity of the radiation falling on a metal surface, once intensity of radiation that is falling on metal surface is below the threshold frequency, in that case no electron, okay, is ever emitted from that surface. Now the third fact is that the number of photon electrons emitted per second, the number of photon electrons emitted per second is directly proportional to the intensity of radiation. Okay, the number of photon electrons emitted per second is directly proportional to the intensity of radiation, meaning that the higher the intensity of radiation, the more the number of electrons emitted, and the lower the intensity of radiation, the lesser, okay, or the lower the number of photoelectrons emitted. So this part is very, very vital. Okay, so let's move to the next slide. Now this is just a diagram, okay, of a device known as photocell, and this device finds application in burglar alarms, automatic doors, photometer, TV, camera, etc. When the maximum kinetic energy of the photoelectron are plotted against the frequency of the incident light for a given metal, the graph is shown below. Okay, so this is the graph of maximum kinetic energy of electrons against the frequency of electrons. So let's move to the next slide to explain what is going on in this graph. Okay, so the straight line graph cuts the frequency axis at F0. And F0 is known as the threshold frequency of the metal surface. Now remember that we said anything below this frequency, no electron will be emitted from this metal surface. Okay, so the maximum kinetic energy of photoelectron is given by K dot A mass is equals to 1 over 2 mv square mass, where m is equals to mass of electron, v mass equals to maximum value of the photoelectrons. So at the anode, the kinetic energy of the electrons equal 0. Okay, so this is where we draw the curtain for the preview of today's video. I hope you enjoyed it, but you can enjoy the complete video by simply clicking on the link in the description below, and that will take you to my school website. So on the website you have to subscribe to enjoy the complete video, and we have a lot to talk about in the complete video. So in the complete video, you will learn about thermonic emission, you will learn about cathode rays, okay, what they are, their characteristic, you will learn about X-rays, their types, and many more. Okay, so I believe you enjoyed the preview of the video you just watched. If yes, please do not forget to hit the like button, click on the subscribe button, and lastly, tap on the notification bell to get informed as soon as we upload the next video.